Hi, welcome to Peniel Educate. In this physics video series, we'll be looking at motion. All right, and I'm expecting that at the end of this video series, you should be able to understand speed as a scalar quantity, while velocity and acceleration are vector quantities. I'm also expecting that should be able to calculate the resultant velocity using a simple example of motion of objects. We'll also be looking at velocity time graph, and we'll complete this video, while we explain the terms used in equation of motion. All right, so what is motion? Motion involves a change of position of a body with time. So we also be looking at motion in a way that what makes body to move and how things move. Okay, so and in this way we'll be looking at some types of motion. We have random motion. Random motion is just all about motion moving, objects moving irregularly or at random, or we can say movements of object haphazardly, with no preferred direction or orientation, no specific direction. So as a result of these movements, the particles collide with one another. So one example that we can say is Brownian motion, right? So look at a regular motion of particles of various kinds suspended in water. It could be of smoke particles suspended in the air, or motion of gas particles. So you know that all these particles move, here and there. Another one that we could talk about is when you burn a bush. If you've been to farm before and burning bush, you will see that there are smoke coming out of such bush burning exercise, and you see the smoke, the objects suspended just moving here and there, colliding with one another. So this is an example of a random motion, no specific orientation, no preferred direction. So the second type of motion that we'll look at is translational motion. So when a rigid body or a rigid object move from one point in space to another, so without rotating, so the motion is said to be translational. And one thing that you need to know is that in translational motion, every point in the body remains relatively fixed to one another. For example, if a car is moving from one station to the other, if a car is moving from one station to the other, or we can say a car is moving from say Lagos to Abuja, it's moving from one place to the other, you don't expect that car, which is an object, to be somersaulting while moving. So it's just moving maybe from Lagos to Abuja, from one station to the other. That is translational. All right. So you can also have another example is a diver. Okay, you can have a diver on a diving board just jumping up, and down, or just jump up and down before, going inside the water. That kind of motion is also translational. You can have example of say a bee flying from one flower to another. All right, so that is an example of translational motion. Okay, so we also look at rotational motion, and the rotational motion, when we have all points in the body move in concentric circles. So we have points in the body move in concentric circles, we'll say that that kind of motion is rotational. Okay, that kind of motion is rotational. So we can say of an example we can say is a wheel of a car, of a car moving, car moving. So we know that there should be a center of these circles, all lie on a line called the axis of rotation, right? So for example, if you have a blade of fan, you can have a blade of fan moving, and you have a center. So you can have this as the wheel. All right, so we have an axis. Okay, we have an axis in which all the blades rotate. Can have an axis, so we have the center of these circles, which is called the axis of rotation. Okay, so another example of rotational motion is the head rotating about its axis. We know that the head rotates about its axis. Okay, so another example of motion is oscillatory, or we call it vibratory motion. So when a body moves to and fro, reversing the direction of its motion and returning regularly to its original position. So we said that kind of motion is vibratory or oscillatory motion. So such a motion is periodic because it repeats itself. An example is that you can have a motion of a rocking chair. You sit on the chair, you just rocking, and you see that the chair is swinging back and forth. So you can also have motion of a pendulum as it swings back and forth. So that is oscillatory or vibratory motion. So another thing that we need to consider while we look at motion is the relative motion. And one thing again that you need to know here is that we may define motion as a change of position, but we need to understand that it is impossible to determine the change of position without a point of frame, or we call it a frame of reference. So we need to determine, when you are talking about change of position of a body, then we need to look at in reference to what exactly do we mean, where exactly is the body before. So and we normally look at a body at rest before we say, okay, this body is changing from being at rest and is now moving at a particular rate. So we always ensure that every measurement must be made with respect to such points of frames or reference. Okay, for example, if you are sitting in a train traveling past your friends standing on a railway platform, so you will discover that there is a relative motion or separation between you and your friend. You discover that you are just moving and your friend is moving backward. For example, also, if you are traveling in a school bus and you look outside, you see trees, moving. Now, this illusion of moving trees is due to the relative motion between, you seated in a bus and the stationary trees. So we know that trees do not move. All right, so that is relative motion. Another example is that you have a body on the surface of the earth. It may appear to be at rest. For example, you have somebody just seated in a position and you say, oh, this person is not moving. All right, but that is only because the person that is observing that body at rest is also on the surface of the earth. So, and the earth itself, together with both the body and the observer is moving in its orbit. So we know that the head rotates, moving its orbit around the sun, and it's always rotating on its own axis all the times. So if you have somebody maybe in space and looking at the same body on the earth, you will see that that body is actually moving. Okay, so we always ensure that every measurement is made with respect to a point of reference, or a point of frame. Okay, so all measurements must be made with respect to frames of reference. Okay, so that is relative motion. Okay, so let us look at some definitions before we go further to explain other things. All right, so displacement is defined as distance traveled in a specified direction, and the displacement is actually a vector quantity. Now, there's something that I want you to understand here, that position of a point in space is actually determined by its distance and direction from other points. Okay, so we should know that the position in a space is determined by the distance and direction from other points. Now, displacement, as we discussed earlier, is about the distance traveled in a specified direction, and we said it's a vector quantity. Now, vector quantity, they are quantity. Vector quantity is just any quantity that has both magnitude, which is the size, and direction. It has a magnitude and has a direction. Okay, so we have velocity. Velocity is a vector quantity. Acceleration is vector quantity. Force, momentum. Why are all these vector quantities? Because they have a magnitude as a size, and we have direction. They have magnitude and direction. All right, so why we have a scalar quantity, it's just a quantity that has magnitude only, so the direction is not taken into account. All right, we have speed. When you have speed, you don't need what direction is the speed. So, we have temperature. Okay, so you don't need a direction of energy, you don't need direction of pressure. All right, you don't need direction of temperature. So those are scalar quantities. So the magnitude generally refers to the quantity or distance. So in relation to the movement, we can correlate magnitude with size and speed of the object while traveling. So that is magnitude. All right, so while the object is traveling, we can say that, okay, this is the size, so and this is the speed of the object. All right, so the speed is the distance traveled in unit time. The speed is distance traveled in unit time. If an object travels equal distance in equal intervals of time, then we say that object is said to have a constant or uniform speed. I'm still going to explain this further in the next slide. Okay, but speed is distance traveled in units of time, and it's a scalar quantity. Why is it a scalar quantity? Because the direction is not taken into account. All right, so velocity is the rate of change of displacement with time. Okay, so if displacement is a vector quantity, velocity is the rate of change of displacement, with time. And we have acceleration is the change of velocity, okay, with time. All right, let's move to the other slide. All right, before we go to the other slide to further explain displacement, let us look at certain examples. Imagine we have somebody walking 500 meter to the east. We have our north, south, east, and west. So you have somebody walking a 500 meter towards east, and having done 500 meter towards east, he then he then turn around and walk back towards west uh, with a distance of 300 uh, meter. Okay, so we can say that the total distance covered is actually 800 meter. Okay, but the displacement is actually 200 meter. Okay, since it's now only 200 meter from the starting point. It started here, move like this, 500 meters. Then from here it returns again to this 300 meter. So this is just the displacement of 200 meter from the starting point. Okay, so that is the displacement. All right, so let us now go ahead and look at further explanation when we're talking about speed. Okay, so now we discussed in the previous slide, speed is the rate at which a body covers distance in respect to time. All right, so the average speed over the distance s is written as this. This average speed, is distance over time. So, for example, if we have a bus covers a distance of 300 kilometers in 3 hours, so we can say this is the distance and this is the time. So over say 3 hours, that is let's say it's over 2 hours rather. So we have 300 over 2 hours, then that is will give us 150 kilometer per hour. All right, so but the SI unit of speed is meter per second. So you can either convert the time to seconds, then the kilometers to meter. You can convert that and you have your answer in meter per seconds. All right, so now when a body covers equal distance in equal time intervals, no matter how small that interval may be, that time interval, no matter how small it may be, the speed is said to be a uniform speed, or we call it a constant speed. Okay, so when you have a body, probably maybe within let's say within 2 hours, it covers 200 kilometers. Then in another 2 hours interval, it covers another 200 kilometers. So you see that equal distance is using equal distance and it's using it's covering it in equal time. So that means that particular body is moving in uniform or a constant speed. Now, velocity and speed, they are often used interchangeably. But in speed, like we said, speed is a scalar quantity. No direction is specified. Okay, but in velocity, it is necessary to specify direction because velocity is a vector quantity, and in vector quantity there must be magnitude, which means by size, and there must be direction. So since we have velocity, displacement, which refers to uh, distance covered in a specified direction. So, and we have velocity, which we have defined as in terms of displacement. We said the velocity is the change of displacement with time. So, velocity is also measured in meter per seconds. Now, when a body moves with equal displacement in equal time interval. So no matter how small that time interval may be, the velocity is said to be a uniform velocity or constant velocity. All right. So it means that when you have a body moving with equal displacement, you move from here to here, maybe 200 meter. Okay. Then you move again from here to here, in 200 meter, and you are moving uh, in equal time interval. Maybe you move this display, you just move from here to here, you move in 2 seconds, you move from here to here, you move with another 5 seconds. Okay, so that is a uniform velocity. However, when an object covers unequal distance in equal intervals of time in a specified direction, the direction of motion, if the direction of motion changes, it is said to be moving with a non-uniform or variable velocity. All right, so now what it means is that if we have a vehicle moving, a distance of 10 kilometers in the first hour, you are going from maybe Lagos to Abuja. In the first hour, you move 10 kilometers. Then in another second hour, you covers 20 kilometers. You have done 10 kilometers more. So just within another 1 hour. Then after that, you then cover maybe 5 kilometers in the third hour. Probably you have slowed down a bit and all that. So it shows that you are covering different distance in the same interval of time. The same interval of time, you are covering different distance. So that means that body is moving in a non-uniform or variable velocity. For example, a revolving fan at a constant speed has a variable velocity, or we'll call it a non-uniform velocity. Okay, before we move to velocity time graph, let us look at distance time graph. Let's say if we measure the distance covered by a moving object at known time intervals, say 2 seconds, and we plot the values of the distance on y-axis. Let's say we have the distance here on y-axis, right? Distance here on y-axis, and we have the time. Okay, we plug the time on the, which is time in seconds. We plot it on the x-axis. Okay, so with that, if that one is done, this graph provide some useful information for us about the motion of the object, okay, and the speed of or the velocity is uniform. The speed is uniform since we have the body covers equal distance in equal time interval. So the speed is uniform. Okay, so we have speed to be let me do that here. We have speed to be that is distance, which is the displacement. Okay, I'm not actually using this, so I'm not using the velocity time graph. Okay, so probably let me go to other board here. So we have distance. Don't forget, sorry, we have speed rather, speed, okay, or the velocity. We have it as displacement, okay, displacement over time, okay, that's displacement over time. And you discover that the gradient of the slope, that is line AB. Let me go back to where we are. All right, so we have here, we have line AB here, this AB here, this AB here, okay, and the AP here, okay, AP, that is here, AB, that is here. That gradient or slope of that line, is the same or constant along the AB. So you discover that we have the rate of change, that's over the time interval. Time interval here is 2. So you have 5 here, 5 divided by 2, that is 2.5. Then you have the distance here is also 5. So it's actually moving at 5 kilometers. So if you do that with the time interval, it's going to be giving you 5 over 2, 5 over 2, 5 over 2. So we have that slope constant all throughout along this line AB. Okay, so now, but beyond this line AB, beyond this line AB, beyond this line, you discover that that line, that graph is no more straight but curved. So you have a curved line from here, that's from C, D, here. So it's a curved line. So we have a straight line here, just going straight line here, then we now have a curved line. So the speed or the velocity between C and T here, from here to this particular place, for this place, from this C and T, they are no more uniform. They are no more uniform but variables. Okay, they are no more uniform or variables because you have this place decelerating. All right, so and it's decelerating, the time interval changes. Okay, all right, so the velocity of the body, at any instant. For example, if you look at this instance of C here, we just instance C here, okay, instant D here, and instant E, the velocity of the body, is then given by, if we have velocity as C, the gradient of the target is C. Okay, if we have the target here, which is C, we can have tangent C to be XR, this is X, this is X here, XR, okay, over QR, okay, which is QR here. And here also, the tangents, we can have, if we have maybe a P here, we're going to have the tangent at E could be, or if you have, let's put a Z here. All right, we also have a PS. Okay, we have a ZX, rather, a Z S here all over the SP. Okay, ZS over SP. So that is also the tangent at E. Now, the velocity, all these velocity that are changes that are here, the velocity is called instantaneous velocity. All right, so instantaneous velocity is defined as the velocity at any instant of time. So the example that we can talk about is the speedometers of moving vehicles. The speedometer indicates instantaneous velocity. Once you're moving, it just be showing, the velocity that you are moving at the instant of time. We'll look at the uniform acceleration when the velocity of a moving body increases by equal amounts in equal intervals of time, no matter how small the time interval may be. It is said to move with uniform acceleration. So we'll look at the velocity time graph that's here. let's look at the velocity time graph.
All right, so let us consider velocity time graph. Assuming that we are given velocities of an object moving along a straight line, as this table here, we are given velocity at this particular table. Okay, so if you plot velocity on the vertical axis, this is vertical axis, and we have time plotted on the horizontal axis, this is what we have as being plotted as velocity time graph. You discover that velocity here, once is 0, time is 0, that's what's here. Once is 2, the time interval is 1. Once is another 2, that's 4. The time interval is 2. Now you discover that we have a uniform acceleration between 0, 1, 2, 3, 4, 5. Okay, now we have a uniform acceleration, and that's the point this point 0 to a, this particular point, we have a uniform acceleration. Okay, you see that the change of velocity, is in respect to change with time. Velocity is changing with 2 meter per second, and we have time changing in 1 second. And once you get here, this particular 10, velocity remain the same, it's just 10. Velocity remain the same here. So we have a uniform velocity right from here, okay, up to this place. We have a uniform velocity, and that's the point A and B. Then from from this particular one, you have the velocity, going down. After this 10, we have 8, 6, 4, 2, and 0. So we have a uniform retardation. Okay, you also discover that this is actually reducing by 2 meter per second. That's retardation, which is the opposite of acceleration. Then you have the time interval also, reducing by 1 seconds. Okay, so that's one thing that we need to know. So now the acceleration is actually change in velocity. The acceleration is change in velocity uh, over change in time. Okay, now for this particular one, acceleration OA, this OA here, okay, the acceleration OA, let me just write it here, OA will be equals to, which is actually the tangent. Okay, so this particular one, if you want to find this line, then you find this particular one, AD over OD. Okay, it's going to be AD over OD. Okay, and you have AD to be 10. You have it to be 10 meter per seconds all over OD, which is 5. Okay, that's 5 seconds. So you have the acceleration to be 2 meter per seconds. Okay, so the answer is 2 meter per second. Okay, don't forget this particular one is seconds. So by the time you find your acceleration, 2 meter per second square. All right, now the body is said to be traveling with uniform or constant velocity here. All right, it's said to be now because the velocity is uniform over the time interval. For example, I told you that the velocity is uniform over a time interval. Okay, look at the velocity now, is uniform. You see, we also have the time interval to be 5, 6, and 7. Okay, so the acceleration over this period is 0. Okay, the acceleration here is also 0 because the velocity is not changing. Velocity is uniform, so the acceleration is 0, and the gradient of this particular line AB, the gradient of this particular line AB is 0. Okay, the gradient here is 0. Why? Because there's a uniform velocity. All right, so the velocity is the same. Y is just changing with time interval. Okay, so we have the gradient for this particular one is 0. So uniform acceleration is defined as the motion of an object whose velocity increases by equal amounts in equal time interval. However small the time interval may be. So this particular one is a uniform acceleration because the velocity is increasing with equal amounts, okay, and with equal time interval, 2 meter per seconds in every 1 seconds. All right. Now we also discussed that a uniform or constant velocity is the velocity of a moving object where equal distance are covered in equal time interval. Okay, for example, this is a uniform velocity. Okay, so the equal distance are covered. You only covered the 10 that are covered at equal 1 seconds, equal time interval. Okay, so now we can also define uniform deceleration, which means that the velocity decreases by equal amount in equal time interval, right? The velocity decreases with equal amounts. Okay, we have velocity decreasing here. It is 8 to 2 meter per seconds. Okay, the velocity is decreasing by 2 then with equal amount of time, 1 1 1 seconds. Okay, now let us look at variable acceleration. Okay, all right, so variable acceleration, suppose we have a velocity time graph as shown in this particular uh, figure. The acceleration along OA is uniform. All right, we know that acceleration along this particular point to this particular point is uniform. Okay, then we have acceleration from BCE as variable. Why? Because we have velocity, different velocity here, different from velocity here, from here, and it's not increasing with equal amounts of time. Take the time here, it's actually different from the time here. Actually different from the time here. It's not um increasing with equal amount of time. So we have a variable acceleration. Okay, let us move on. I want us to look at distance from velocity time graph. How do we calculate distance from velocity time graph? All right, so let us look at how to quickly do that. Now, in this particular diagram, for us to find the total distance covered from O to C, then we need to know all the distance covered, that is OE, distance from OE, we need to know it. We need to know distance of ED, okay, and we need to know the distance of DC. All right, so for us to calculate the total distance covered during the interval uh, between O, that is this O, and C. Now, for this particular period, this is like a triangle. So the distance covered for this period is like, okay, we'll do the total distance covered is average velocity, average velocity multiplied by time. Okay, all right, so average velocity multiplied by time. Now, what is the average velocity? Okay, half, this is OE, okay, from here to here. The average velocity is half OE, okay, then multiplied by the time interval that is used to cover the 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 period, which is AE. Okay, now this is the AE, which is the interval. Now what we're just doing is that this is just like area of triangle OAE. Okay, so that's one thing to take note there. What you just need to do, triangle, area of triangle said is the half base multiplied by height. Okay, so your base here is OE, okay, which is the average. Your base here is OE and your height is AE. So the distance here is half distance, that's half OE multiplied by AE. That is how to find that one, S1. And don't forget the total distance you're going to get is going to be S1 plus S2 plus S3. You're going to get distance here, distance here, distance here. Once you add the three together, you're going to get your total distance. Now, how do we calculate the distance here, which is the S2? This is just the area of a rectangle, and the area of a rectangle, okay, we have AE, okay, that's AE, okay, AE multiplied by ED, okay, this is just length times breadth, okay, this is length times breadth, okay, that's that is the total distance for that particular one, just the area of the rectangle AB, DE, ABDE that we're looking at there. Okay, so that's how to calculate the distance of S2. What about the S3? This S3 is also the area of a triangle. Okay, so what do we do? You know that this triangles actually have base times height. So what is our base in this time around? We have our DC, so half times DC multiplied by height, which is BD here, BD. Okay, so that is how to calculate the distance of S3. So the total distance of the time interval between 0 and C is S1 plus S2 plus S3. That is how to calculate that. Okay, so let us look at other types of velocity time graph. Okay, let us look at other types of velocity time graph. Okay, before then, we can also get the total distance. We can also get the total distance by looking at the trapezium, trapezium 0 OABC. Okay, if you look at trapezium OABC and the distance, I mean the formula to calculate the value of trapezium is okay, sum of the parallel side, sum of the parallel side multiplied by height. Okay, all right, let me do that again. Okay, like I said, another way to find the distance is to look at the trapezium 0ABC. Okay, and the formula says that half, okay, sum of the parallel sides, okay, multiplied by height. Okay, that is the formula. All right, so half, okay, what is the sum of the parallel side? We have AB, and this is AB, one parallel side, and we have OC. Okay, we have AB plus OC. Okay, that's one parallel side. Then multiply by height, which is AE. This is the height here. AE can be BD, AE is the same thing. AE. So this is also the total distance. Okay, if you really don't want to do the other style, so you can calculate the total distance with this. Now let us look at a ball thrown vertically upwards. Now the velocity of a ball thrown vertically upward decreases uniformly from OP, to 0 as the ball moves up. So if the ball is thrown vertically upwards, it decreases, the velocity move like that, they stop, and when it gets to the highest level, the velocity is 0. When it gets to the so it decreases until it attain a maximum height, when the velocity becomes zero and it starts falling before the ball starts falling. Now, for a motion of a ball thrown vertically upward, when a object is thrown vertically upward, we should understand that that particular object is going to fall back to the ground under the Earth's gravity. So if an object is thrown vertically upward, it decreases, it decelerates, or we say that it undergoes retardation under the Earth's gravity. So its speed decreases until it reaches the maximum height where the velocity will now be zero. So it moves, so it decreases uniformly from OP to zero as the ball moves to the highest level at a time A. Okay, get to the highest level at the time A. Okay, then the ball then increases uniformly. It then increases uniformly. So now increase uniformly, as it gets to the ground at the time B. So the ball undergoes a deceleration or retardation and then an acceleration. So it will undergo a deceleration here at the time A when it's being thrown upward. Okay, then it then undergoes an acceleration when it's coming down, at a time B. All right. Okay, so if we also look at a lift moving from one floor to another in a building. So if you look at a lift moving from one floor to another, you discover that the velocity of the lift increases to a maximum value and then decreases to zero as the lift move from rest, from one floor to another. Okay, so if we have a lift moving from say the second floor, okay, to the third floor, okay, so as it's going to move, maybe the lift just stop some people here on the second floor. Now as the lift move upward, the lift increases, it's going to exercise some uh, uh, um, energy, to ensure that it moves. So it moves upward and increases to a maximum value. Okay, so it moves upward and increases to a maximum value and then decreases to zero. Okay, so it moves, to maximum value, then decreases to zero. That's why it could stop at the third floor. Now the area of OAB here, the area of OAB represents the total distance covered. So right, so this place represents the total distance covered, which is also like the side. These are the total distance covered. So like we said, so the velocity of the lift increases to a maximum height. Okay, then after that it then decreases to zero. Okay, then decreases to zero, as the lift moved from rest at one floor to the other to stop on the other floor. All right, so that's what that is all about. All right, we have come to the end of the first part of this motion, and by the grace of God, next week we'll be completing the second part. All right, I want you to subscribe to our YouTube channel, like this video, share with your friends, share with your loved ones, let them give thumbs up for this video. And we also want to hear from you. You can make comments and you can ask some questions. All right, so we'll see you next week for the concluding part of this topic in physics, motion. All right, thank you. I hope this has been very, very informative for you. See you next week. Bye.